Okay. Well, first of all, thank you very much for kind introduction. And it's a very pleasure for me to come to ICBS. In fact, last year I was also at ICBS, and I'm also organizing some workshops here and there. But this is something of completely different scale. And sometimes if you try to scale it, then the workload scales exponentially. So I know how hard it is. And also, let's see. So, and in fact, I'm very pleased to be back. So this is me, this is me last year. I forgot to take my own photograph. So this year I took my own photograph. Well, let's see. So let's see what will happen but next year. But yeah, and also, of course, I am receiving, very presently, we are receiving a prize. And I'd like to very much take this opportunity to thank my co-authors, Kevin Costello at Perimeter Institute and Edward Witten at the Institute for Advanced Study. And it's such a pleasure for me to learn from, I would say, one of the most distinguished mathematical physicists, literally of our generation. And it's a really pleasure for me to learn from them. And it really was a turning point in my career. And how to even think about the mathematics and physics in general. So let's see. So our paper was this paper, Gauge series integrability, part 1. And it took some time to complete. So I'm supposed to give a talk, a short speech in the math night. So I'm going to talk about a little bit about the story behind this. And so it's 141 pages. And then there's another paper which we put out afterwards, part 2. And I'm very proud of these papers. So let's see. Let's come to the scientific part of the talk. Some of you I know very well, and probably some of you might have heard my talk before. But of course, in the spirit of ICBS, I try to start kind of from scratch. And the point is that some of the basic ideas are pretty simple. And that's the whole point of my discussion. And it is true that presentation-wise, it is true that I prepared way too many slides, and I'm going to flash it. But most of the slides are almost empty. So depending on the content. So you shouldn't be too scared, or if you miss a couple slides, probably, or if you fall asleep for 3 minutes, probably that's going to be okay. Let's see. So what is the motivation? And in fact, I spent a little time on the motivation because I realized that over the years, not everybody shares the motivation, actually. So, well, first of all, this is a session on the mathematics of string theory and condensed matter theory. And then, so it's an interaction between math and physics, happens all the time. And of course, that happens in many different branches of mathematics and physics. But I would say that the integral models is one of the areas where the interaction between physics and mathematics happen. And it's a little bit hard to say if you're an integral model theorist, are you a mathematician, or are you a physicist? And it's actually great that, that people work on different things. And that also means that it's a very diverse area. Very different definitions of integrability, different viewpoints, different techniques, all sorts of motivations, sometimes even application to industry or like non-equilibrium physics. I mean, there are various different aspects of it. And that's why it's fascinating. And so let's see. Well, of course, having said that, I have to, in this talk, at least I have to focus at least some aspect of integrability. And then one of the characterizations is the celebrated Yang-Baxter equation. And it goes back, as the name says, at least it goes back to some version of the Yang-Baxter equation. It might have appeared even before. But at least the version where the Yang was attributed is the 1967. So he was solving the Hamiltonian with the delta function potential. And he wrote down this equation, y equals to y. So it's actually denoted y, actually. Y stands, maybe y stands for Yang, maybe. I noticed that this morning, actually. But now, of course, we use R, right? So, and then yesterday we heard from Andrei Okunkov that R stands, of course, for Reshetekin. Okay, but anyway, so whatever the symbol is, this is the Yang-Baxter equation. And of course, we should also acknowledge that even the name Yang-Baxter equation might be coined by Professor Fadeev. I had a couple of opportunities to talk with him, and he's a wonderful guy. And who unfortunately passed away already. But of course, there's a tradition, Russian tradition, so-called Leningrad School, and many other places on this fascinating topic. So that's the Yang-Baxter equation. And of course, probably most of you have seen already some definition of the Yang-Baxter equation. But it doesn't probably hurt to spend 1 minute or so explaining what the Yang-Baxter equation is. And of course, this graphical equation, the left-hand side equals the right-hand side. And at each of these crossings, so there is, for example, here 1 and 3 intersect. And there you have the endomorphism. Also, there's some vector space with parameter associated with it. And there at the crossing, you have the element of the endomorphism of Bi times Bj. And that's called the R matrix. As I said, R is reciprocal. And then there is a Zi minus Zj, the spectral parameters. Zi, Zj's are associated with the I's and J's line. And the Yang-Baxter equation states that the two equations are the same. So it's essentially the same ingredient, but the product is taken in a different order. So that means that we are doing the scattering, and then factorize it with two-body scattering, and then the ordering doesn't matter. So that's the, so in fact, this is how you get, as close as you get to the statement of Coleman-Bandura theorem, if you know about it, and in 2 dimensions. So if you apply a version of the Coleman-Bandura argument, then you get the version of this. But anyway, so this is the Yang-Baxter equation. It's a celebrated equation. And once you solve it, there is a formal argument. So it says that you can construct many conserved charges and from monodromy matrix and everything. So at least it gives some characterization of the integral model. Now, people found various different solutions of this equation. And one of the first one was typically attributed to the Maguire-Yang. So this is a Maguire-Yang solution, which is a rational solution where R matrix is simply identity plus permutation. And that's the Maguire-Yang solution, which is they found it relatively easily. But then what's amazing is that people found a collection of solutions. And in this particular case, first, the leap found solved the 6-vertex model, which in this one, which is called the trigonometric R matrix. So trigonometric simply means that you have sine, cosines appearing, and the law of addition for sines, and that's necessary for solving this Yang-Baxter equation. Now, what's even more amazing is that Baxter, who was somehow is very familiar with the elliptic functions, could found the elliptic solution, and that's a celebrated 8-vertex model. And these are all amazing discoveries, in my opinion. And so I would also think that even the existence of integral model, that anybody could ever solve the integrable, solve the Yang-Baxter equation, seems like almost magic to me. So actually, so not everybody shares this sentiment, but that's certainly my sentiment. So if you just try to now count how many variables there are and how many equations, there are way more equations, for example. So there is a certainly over-constrained equation, at least if you do the naive counting. So if you just try to solve it randomly, I don't think there is any hope of finding the solution, which is related to the fact that if you take a random physical system, it's not integrable. Most of the systems are chaotic and things like that. Integral models are very, very special. So why there is any integral model at all? Isn't that a miracle? That's always the sentiment I have. But of course, not everyone shares the sentiment. And then sometimes if the integral model experts, for example, telling me that, for example, okay, well, what are you saying? What are you talking about? So, I mean, just a solution Yang-Baxter equation, right? So you just prove it, right-hand side equals to left-hand side. And that's it. So then no mystery whatsoever. What are you talking about? Are you philosophizing? And so there are a lot of people say that. And of course, that's a legitimate attitude to some extent. But sometimes, I mean, for me, sometimes even just verifying it is not enough. And I want to understand it. And so first of all, how do we know? Suppose that we don't know anything, but want to start from scratch. How do we find the solution to the Yang-Baxter equation? And then so that we can, even for the existing solutions, can we find them in a better way? That's the question. At least I'm a type of a mathematician / physicist who cares about these questions. And I'm not forcing you to think that way, but that's the case. And in fact, I noticed that over the years, I'm not the only one in the mathematics community who cares about these questions. And this is an example. So called Aira. And unfortunately, his Japanese is so beautiful. So I hesitate to translate. But at least the last meaning is that, so I'm a little hesitant to translate it. But at least what it says is that okay, I usually try to follow each individual step of the proof very, very carefully. Because otherwise, he feels that he doesn't understand the theorem. And that means that there's more than just verifying it, right? If it's verifying it, you can just let the Lean or something, some other program to verify it for somebody else. You don't need to do it yourself, right? And it's checked. So who cares? Well, who cares about the details of the proof? But he cares about each individual step of the proof precisely because he feels that there's something just logically correct behind it. That's what Kodaira says. And then this, I'm very sympathetic with statement. And of course, well, some of you, I know some of you are physicists, and they say, no, Kodaira, okay, I don't care, maybe. So in that case, I can bring in the Feynman, your favorite physicist. And, Feynman is extremely famous for trying to understand everything himself. And there's a very famous mantra. It says, what I cannot create, I do not understand. So if you understand it, I should be able to create it, hopefully from scratch. And that's exactly the Feynman philosophy. And in fact, this is the appendix of his Feynman lectures on computation. And what he says is that, in fact, in his late years, he was very interested in integrable models. And in his task was to study the 6-vertex model. And then he gave it the problem to students, you should solve it. And then he solved it himself, like, oh, okay, I'm great. But of course, there's an even more difficult one, 8-vertex model. He spent time and time in trying to reproduce 8-vertex model, and then he didn't succeed. So that's an anecdote which says that at least Feynman thought that 8-vertex model is miraculous, he never understands it, and also I share the sentiment as well. So that's the type of things I do care about. Well, of course, if you're a professional mathematician, you already know some framework to understand it. And that's this Yangian, infinite dimensional symmetry. So Yangian was defined by Drinfeld, and it's in this amazing, amazing paper in 1985. And it's a very short paper, but it actually includes many of the ingredients which I'm starting to struggle to understand. And in particular, he already has the defining equations of the Yangian. And in particular, there's this equation number 4, which looks complicated. Commutator, 2 commutators, commutators of commutators, and then there's this cubic term. So he has this miraculous relation. Well, of course, he could do a little bit. He could derive this because there was already a solution to Yang-Baxter equation. And then he cooked up the algebra from there. That's how he found the solution. But of course, once you have the algebra, then it's a familiar territory if you're a mathematician. So algebra, and then do the representation theory. Or maybe Q deform it, or elliptic deform it. And that's exactly how the things go. So it turns out that the 3 hierarchies, rational, trigonometric, elliptic solutions of the Yang-Baxter equation, simply correspond to some representation of the Yangians, and then Q deformed version, Q and further deformed version, quantum affine and elliptic algebras. And those are the simplest solutions. So these are roughly associated with SL2 and a spin half representation, 2-dimensional representations. So now in a sense, what needs to be done is clear. We have the algebra. So that's your starting point, and then just do the representation theory. Of course, that's a very, very complicated story, and it's a very intricate representation theory. And especially at root of unity, it's fair to say that we don't have a complete understanding. But anyway, that's how if you're a typical mathematician, that's how you start this. So your professor gives you the defining equations, and you're supposed to memorize it. and then that's the definition 1. And then you start your research from there. Okay, maybe it's such exaggeration, but it might be one way to do that research. Which is completely fine, except that my viewpoint is a little bit different. So, okay, that's great, but how could I even remember that complicated relations? So I'm terrible at remembering anything, so how could I even remember that? Or at least, even if I remember, how do I understand it? So I like to understand it from something more fundamental. And of course, there's not a unique answer. There are various different viewpoints, and depending on the viewpoint, people will have a different answer. But that's, at least for me, one of the ingredients is quantum field theory. So if you start with quantum field theory, that's something you know very well as a physicist, and then try to reproduce the integral models starting from there. So that's what I want to do. And of course, that sounds like an ambitious thing. And I need a good role model. And if you're a mathematical physicist, you know that there is a very, very good role model. That's the Witten's explanation of the Jones polynomial. from three-dimensional topological quantum field theory, which is the Chern-Simons theory. So of course the story goes like there is a knot, and then you typically consider the projection and define it. But Witten gave an intrinsically three-dimensional description so that you don't need a projection. And that also led to many other developments. And one of the developments was the connection to the quantum group. So in the case of integrable models, there was Yangian and quantum affine algebra. That was algebra. In the case of this knots and three manifolds, one of the defining symmetry was the quantum group, the Drinfeld-Zippo quantum group. And the story goes like basically, if you start that as an input, you can define the invariance of knots, tangles, and the three manifolds, and that's the celebrated work by Reshitik and Turaev. So to some extent, the story was there. And in this particular case, of course, Witten tried to explain the quantum group. So he had a paper trying to explain quantum groups from gauge series. So it started with the Chern-Simons theory. He reproduced the quantum group. And then if you're mathematicians, and then you can try to construct the invariant of knot, which coincides with the partial integral representation of the so-called WRT invariant now. So things work beautifully in this case. Well, you reproduce he tried to reproduce some of the commutation relations of the quantum group. And in the logic somewhat similar to what I'm going to present. In fact, please ask questions. Please ask questions well, let's see. I mean, these are the Wilson lines, and then you try to see what type of coupling the Wilson line to the bulk gauge field, and then do a version of the loop computation, which is somewhat similar to what I'm going to do. Some understanding was lacking back then, for example. So these days, you might say that, for example, category line defects, and that just gives a representation category. And then you might have to do Tanaki reconstruction, for example, to reproduce the quantum group itself. So you get more like a lep of the quantum group. Well, let's see. No, I have you can try to reproduce the co-product, for example. So, and in fact, basically you have the two Wilson lines, for example, here in parallel. And then I try to do the perturbation theory where there's the gluons in between, for example. And then you try to define the product by bringing it together, for example. And then so at least you can define it perturbatively in H bar. That's in fact what we did is actually analog of that then. Actually for this particular problem, it doesn't work too well in the sense that typically people are interested in rootability and all that, which is beyond the perturbative regime. So in that sense, it was a little bit of a I mean, so moral of the story works, but not everything I have in mind is refreshed too much in this particular old work, I would say. So not everything is there. So maybe, strictly speaking, it might be a little bit too much to say that there is a derivation. But at least he has a paper where he discovered some aspect of quantum group. And so the triangle was there, at least. So that's for the knots and three manifolds. And of course, Witten knew about the integral models. So he tried to, I mean, he succeeded in knot theory. So he obviously tried to succeed in integral model as well. But he acknowledges that he was not successful. And in fact, towards the end of this paper, the previous paper, he said that one of the compelling questions is to understand the origin of the spectral parameter. The spectral parameter being the parameter inside the argument of the R matrix, which is very critical, crucial for integrability. So he didn't succeed in the explanation of integrable models. And in fact, if you look at the literature, people, of course, knew the connection to integrable models. For example, Jones, the work with Jones was partly inspired by that in temporary leaf, etc. But one way of saying that, well, formulating that, at least one thing I learned when I was actually when I was a student, is that there's a connection between integral models and knots. But that is to just send the spectral parameter to infinity. So namely, in the Yang-Baxter equation, there is a spectral parameter. And if the spectral parameter somehow drops, then you get the Yang-Baxter equation, but without spectral parameter. And that's exactly the ingredient needed to make a knot invariant. So what people did back then is to start with the integral model. So I learned it from this paper, review by Wadachi et al. And then, so take an integral model, and then takes a spectral parameter, eliminate the spectral parameter by sending the spectral parameter to infinity. well, things diverge, you have to regularize, etc. But that's exactly what we did. But of course, that feels a little bit unfortunate, right? So you have something with more data, and then somewhat artificially eliminate the data to get a not invariant. So that really smells like something should be there before taking this limit. And in fact, that was also acknowledged in the Whitney interview performed by Toru Eguchi in 1990. Again, sorry, you cannot see it probably. And, but anyway, it's in Japanese, don't worry. And then, let me read it. So Whitney says that one of the problems that have been preoccupied in the past 2-3 years is the problem of the so-called spectral parameter in integrable lattice models. So the vacuum expectation value of the Wilson lines in Chern-Simons theory can be computed in various different methods, but the methods using integrable lattice model, which was first attempted by Jones, sends the spectral parameter to infinity, just as I said. But in order to understand integrable models more deeply, you need to take into account the spectral parameter as a crucial ingredient. So he certainly acknowledges that. And that was 1990. And surprisingly, in the afterwards, nobody took on this issue, at least as far as I know. The problem was open. And honestly, when I was a student, I didn't even know that there was such a problem. If you Google integral models, Yamazaki, etc., you encounter hundreds of papers. But it doesn't necessarily mean that this problem was solved. And in fact, but interestingly, Witten came back to Japan on the occasion of his Kyoto Prize in 2014, and we did an interview. This is me, I was younger. And, and this is a very good interview, and he acknowledges that. But I would say that specifically the kind of explanation I was looking for is what Costello found. So after 25 years, Witten finally acknowledged that there is now a solution. And that solution is a solution by creating Costello in the celebrated paper. So this one really solved the problem. And that's a fascinating story. But at least for physicists, like at least when I was talking with Ed, I found the story a little bit unsatisfactory in the following sense. So he did completely correct thing, and even more fascinating things, including the Cauchy duality and all that. But to some extent, I'm an old-fashioned physicist, at least part of the day. And then, let's see, it's great to invoke Cauchy duality, etc. But let's see, if you're an old-fashioned physicist, isn't it a little bit too highbrow? So what we want to solve is that, okay, Costello identified the gauge theory, right? And then it should be that you don't need to invoke any fancy mathematical ingredient. It's just a field theory, so just quantize it. If you know a physicist, you should be able to quantize it. And that's what we try to do. And that's what we try to do in our paper. So let me try to come to the basic idea first, and then try to incorporate the various different ingredients. Certainly, I'm not going to explain all the details, but try to highlight some of the main ideas. As I promised, the basic idea is extremely simple. And by hindsight, it's a little bit hard to imagine why people have trouble coming up with this in the 25 years. People do much more sophisticated stuff in all sorts of mathematics literature, but this is extremely basic. But maybe it doesn't necessarily mean that it's easy to find it. So the theory I'm going to discuss is this four-dimensional Chern-Simons theory. It's defined on sigma times c, where each of that is a two-manifold. And let's see, two-manifold times two-manifold. And this omega is a holomorphic one form on this C, on this manifold C. It's a one form, and then there's a Chern-Simons three form where there is a connection A. So this is the four dimensions, but this A itself has only three components actually. So locally, this omega can be written as ZZ, where Z is a holomorphic coordinate on the C. So it's almost like a three-dimensional Chern-Simons theory, but it's a holomorphic version. And people knew this kind of structure. For example, there's a WZW, and there's a 4D Kähler WZW, which takes a similar form, or et cetera, et cetera. People know a version of this. But what's peculiar about this system is that on this product of two-manifold times two-manifold, two of the directions are topological, whereas the two directions are holomorphic. And there is a holomorphic direction with a holomorphic coordinate, and this direction will play the role of the spectral parameter of the integrable model. And as an object observable, we consider the Wilson line, just as in the case of the 3D Chern-Simons theory. So it's a line, a holonomy of the gauge field, located at a particular point in the spectral parameter. So the line is equipped with a parameter. Now, there can be other lines. For example, instead of vertical direction, there could be horizontal direction. And then you can make a lattice out of it. So the statement is that this figure, which really looks like a lattice, is actual integrable lattice model. So in other words, if you compute the expectation value of this pair of Wilson lines, that coincides with the partition function of some integrable lattice model. And that's the statement. And of course, you can see that it requires a little bit of argument why it's a lattice model, etc. But the most crucial point is that it's integrable. Namely, it satisfies the Yang-Box equation. And the reason is pretty simple. So this is one side of the Yang-Box equation. But now the theory is topological, so you can move these lines around. And of course, you can move these lines around to cross it. So the theory is topological, so you can move these lines around. And then that's the Yang-Box equation. And this is very similar to Witten's explanation that things are topological 3 dimensions, so you can move the links around, and you get the Leiden-Meister move of the node. Well, of course, you might potentially worry that something nasty might happen when everything collides, but they seem to collide only in this direction, and they are well separated in the holomorphic direction in general. So there is no weak singularity or anything to worry about. So this is a conceptual explanation of why you get a solution to the Yang-Box equation. Now, the point is that now that we know that you have a solution to the Yang-Box equation, you get an integrable model. Of course, then the next question is which model, which R matrix. And there's a very good way to compute it. Well, of course, the R matrix is associated with the crossing of 2 lines. And at the crossing of the 2 lines, we have lines like this. But in quantum field theory, there are quantum corrections, so-called, represented by Feynman diagrams of this type. And the statement that if you sum up all these Feynman diagrams with H-bar expansion, where H-bar is a Planck constant, then you get the R matrix. So that's the statement. Now, so you might worry that in order to get the R matrix, you have to do all the computations, H-bar squared, H-bar cubed, involving 1 loop, 2 loop, 3 loop diagrams. And in principle, it could be. But fortunately, we already know that it solves the Yang-Box equation. And Yang-Box equation, if you expand it in H-bar, has a recursive structure. So if you first solve the first order equation, and then actually all the higher order terms are determined sequentially. So you can make it an argument, some of which is splashed out in our paper in part 2. And the diagram for the first order correction, first order non-trivial correction is very simple. It's a 3-level diagram. And you just do the computation to get this expression, which is known to be the first order H-bar expansion of the R matrix, known as the classical R matrix, which coincides with the answer known in the literature. Now, so this is essentially the result. Now, so I get the classical R matrix, but associated with the plot. Well, we have to specify the gauge group and then the representation. But it's also another choice, which is a choice of the spectral curve. I said it's just a curve, but what's the genus, or is there any puncture or not? And then there's an argument, which I won't explain too much, but which says that I don't want this holomorphic one form to have a 0. And you can try to debate why it's necessary, but the rough explanation is that this omega appears in combination with H-bar, and I'm doing an H-bar expansion. So when omega has a 0, it all looks like H-bar goes to infinity around it, at least locally. And that's bad for perturbation theory. So that nails down to the possibility that omega has no 0. And it's elementary exercise to show that if the holomorphic one form has no 0, and then there are all these 3 possibilities. So it's C or C star or elliptic curve. And these reproduce the rational trigonometric elliptic classification. And indeed, purely in the language of Yang-Box equation, there is already a classification under some assumptions of the solutions of the R matrix, which has this H-bar expansion of this form, known as the quasi-classical R matrix. That's been classified. And what I'm presenting now is a different argument, in fact, much simpler argument for reproducing that classification. In fact, this is a paper, but published as a book, actually. It's like 100 pages or so. It's reasonably complicated if you try to go through all the proofs. And then, so you can try to go even further, like in the elliptic case. In general, there is some variation of the Yang-Baxter equation known as the dynamical Yang-Baxter equations, and how to incorporate that, etc. But maybe that's a little bit technical, too much technical detail. So rather than going into some detail, next we should discuss the Yangian, right? So because Yangian is the ingredient for doing the representation theory. So how do you get the Yangian? That's one of the most crucial parts. And we actually provided a series of arguments. But let me provide one argument. Well, first of all, what is the Yangian? So Yangian is some H-bar deformation of the universal enveloping algebra of the Lie algebra of the gauge group with the extra parameter, formal parameter. So it's a formal parameter, formal power series. So this is the H-bar equals 0 version of the Yangian, and there's some deformation to the Yangian. Now, why you get this? That's the first question. And there's a counterpart of that here, which is that in this Wilson line, typically what you get is the A here. That's the usual Wilson line. But it turns out that this integral is only along the topological direction. We are not doing the integral along the spectral curve direction, so you can actually take a holomorphic derivative and expand the holomorphic coordinates. So you have a power series in Z. So there is Z0, but if you set it to 0, you get the element here. So first of all, classically, you reproduce this. So the fact that you have a formal parameter Z is a general feature of the fact that we are considering holomorphic theory. So it's a holomorphic theory, so you have a holomorphic dependence. Now, I want to see how to get the Lie algebra first. Because before coming to the Yangian, I first need to explain how to get the Lie algebra. Well, of course, people are familiar with the Lie algebra here, but the point is to try to get why the Lie algebra is necessary. We are usually not taught to think about that way, but there is an explanation of that. And roughly speaking, the story goes like here. So here, this is a Wilson line, and then there is a gauge field coupling to it. And then there are various different contributions here and there. And the thing is that, for example, suppose that there is no such term. There is a cubic term in the non-abelian in this Lie algebra. This F is a structure constant. And in this case, you can show that in general, because these two things don't commute, if you do the gauge variations with respect to the external field, the variation is not 0. So whatever it is, it's an external field, and it won't gauge invariance. So if you do the gauge variation, the answer should be 0. But unfortunately, because these two terms don't commute in general, the answer is non-zero. If you just take these first two terms. And that problem is resolved if you take this extra term, which cancels this contribution. And that's why you need a Lie algebra. And in fact, you can repeat that. And the Jacobi identity, celebrate the Jacobi identity, you can derive from some expression like this. Now, that's clearly a classical theory. What happens in the quantum theory? And that involves a detailed analysis. There are some diagrams, one loop, two loop, counter terms, and everything, which is complicated. So it requires a cohomological analysis. But in the end, we encountered one particular diagram, which looks like this. And it turns out that this diagram, this particular diagram gives rise to the right-hand side of this complicated right-hand side of one of the defining equations of the Yangian. So this is one of the terms when you compute such couplings. So previously, it was a classical correction, classical computation. So there are 3 A's outside. And here, I'm doing the two-loop computation, so it involves a more complicated diagram. But then it gives rise to this term on the right-hand side, and that's precisely what you get in the Yangian relations. Yes? Yeah, thank you for asking. So indeed, right, so here I'm talking about the Yangian, which is a rational case. And if you go to a trigonometric case where the spectral curve is like a cylinder or C star, then there's an extra parameter. You can think of it as the radius of the cylinder, for example. And then that gives like the Q deformation parameter. And so the Yangian is promoted in that case to some algebra known as the quantum affine algebra, which contains the quantum group as a finite dimensional part. Yeah, so that it comes from the spectral curve direction, yes. And then, so if you want to go to the elliptic, here is further modulus of the torus tau, for example. And that's how you get the tau of the elliptic algebra. Yes. Well, let's see. I mean, to some extent, yeah. So yeah. I mean, in fact, the rootability is very subtle. And if I have time, I'll comment on some version of that. And so the thing is that we are doing perturbation theory in this approach. So, well, in fact, and then if you do a perturbative approach, it's not necessarily easy to come to the rootability limit with a very finite h bar. Yeah. So, okay, I said h bar is a different parameter, but it's also dimensionful, and you have to take a ratio, etc. So these parameters are related. And but anyway, so yeah, so it's a non-trivial question, and in fact, that's somewhat related to the fact that if you consider the rootability representation theory, I think a lot is unknown as far as I know. Well, of course, there are some results. For example, the continuing and cuts, for example, they looked at some of the central elements. So there are a lot of central elements in the algebra, for example. And for example, when you do the intertwiner for the tensor product representations, the central elements should match, for example, and then that gives rise to non-trivial constraints. And if I have time, I'm going to mention Kyler-Potts model, etc. And then that subtlety is related with those subtleties, that you have an emergent central charge. So so the rootability is very, very subtle as far as I know. Okay, so that's how you get the Yangian. Now, so that's a brief recap of how do you get integrable lattice model. So I have a lattice, right? So lattice model. And then when I talk with some integral model experts in the more mathematics audience, that's all there is. But if you talk with a physicist and like application to ADS-CFT, etc., all they're talking about the integrable coset sigma models and things like that. So these are integrable field series. And these are slightly different things. And then that we discussed in part 3 of this paper with Kevin Costello. And again, the idea is extremely simple. So previously, we have a collection of one-dimensional line defects. And that's why you get the one-dimensional lattice. Well, two-dimensional lattice, because it's two directions, but one-dimensional object. But if you want a quantum field theory, you should have two-dimensional object. So now, this defect fills the whole of these two dimensions. It's no longer topological, depending on which defect you consider. And these are located at different points in the spectral curve. And what type of defect is it? But before coming to that, so, and then there's a nice argument which says that the resulting theory is integrable, at least classically, for a slightly different reason. So let's see, why is that? So first of all, what do you mean by resulting two-dimensional theory? So the theory we have here is the two-dimensional defect coupled with the four-dimensional theory interact with each other. And then I try to integrate out the theory on these four dimensions. In other words, there's a bulk gauge degrees of freedom, and you integrate out. And you get the effective theory in two dimensions. And this theory, you can argue, is the classically integrable at least, because there's an equation of motion of the Chern-Simons theory, which says that some connection is flat. It's a version of the Chern-Simons theory, some connection is flat. And if you reduce to two dimensions, it still says that something is flat. And that's not the Lux connection. So if you have a field theory with this flat connection with a dependent spectral parameter, then you declare it to be classically integrable. So that again follows somewhat automatically from the classical equation of motion. Now, of course, this sounds a little bit abstract. So what type of field series do we get? And of course, that depends on what defect you consider. But the defect I consider is extremely simple. It's a free theory. And not even the full copy of the free theory, but the chiral half, for example. Chiral for the fermions. If you like a Dirac operator. So chiral fermions and anti-chiral fermions. Free theory, no interaction whatsoever. So without the bulk, these are completely free theory, no interaction, nothing interesting happens. But the thing is that there is, so these are separated. They don't talk with each other as it is. But there is a mediator, which is the gauge field. So you can let the gauge field, so these guys, each of these guys, they don't talk directly, but they're willing to talk with the gauge field, who is very kind enough to convey the message to the other side. And then if you do that exercise, you get that there's a four fermion term generated. And that's the interaction term for the Gross-Niveau type model. And in this case, the defect is in itself as a two-dimensional theory with a specific Lagrangian. You can do other things, something called a disorder defect. Disordered defects are simply the singularities of this omega. For example, there is this holomorphic one form omega which has singularities, poles and zeros. And you can argue by solving the gauge field along this direction that you get a principal Carter model coupled with the Wess-Mino term. And this is actually somewhat similar to the derivation that you get the Wess-Mino-Witte model on the boundary of the three-dimensional Chern-Simons theory. It's a kind of uplift of that. But now you have this picture, you can actually generalize it further by having a spectral curve with a very, very high genus with many, many punctures. And we in general can argue that they give rise to interesting integrable field theory. And of course, if you try to solve it in practice, that involves the Green's function on this higher genus Riemann surface, complicated, but nevertheless, conceptually, you can do that. And in fact, not just obtaining it. For example, now you have the Riemann surface. There is a moduli of the Riemann surface. You can change the shape, which should look like a deformation of the integrable field series. Integrable deformations, yes. Yeah, here it's a holomorphic direction, yes. Yeah, not vanishing, right. So let's see. So the logic was that the not vanishing, yeah, in fact, thank you for pointing that out. Yeah, so in fact, the logic was that omega not to have a zero when we want the topological invariance of the theory. So in order to explain the Yamazaki equation, it's crucial you can move the lines around. And that requires a topological invariance. And that in particular means, for example, if you put say, let's call the topological direction W bar, for example. And because I want the diffeomorphism invariance, when I said, so because W component of the gauge field is 0, W bar components of the gauge field is 0 because they are related by diffeomorphism, etc. So that puts constraints on what type of boundary conditions we can impose. But now here, we are not necessarily trying to come up with the topological theory. In fact, the defect itself is chiral fermion, which manifestly breaks the topological invariance. So it's a holomorphic theory already, the defect itself. And in that case, there's more degrees of freedom. So you can allow the holomorphic, so for example, if there is a W and W bar component of the gauge field, you can set one of them to 0, for example. And that gives more degrees of freedom. And that's allowed because now I don't care about the topological invariance per se, but more interested in the holomorphic holomorphic conditions. So, well, of course, even in these situations, if you're away from the defect, you kind of still have a bulk, which has a topological invariance. So you can try to have a line defect together with a surface defect and things like that. But at least as a full theory, it breaks the topological invariance by construction. So the short answer is that depending on what you want to do, you have to think about the different setup. Mm-hmm. Yeah, that's right. That's right. So yeah, yes, that's right. So in fact, partly because of that, my previous explanation was not completely rigorous, actually. So yes, you might think, what happened to that, for example? But yeah, so that explanation is not completely rigorous. So yeah, I think I like that explanation, but it's somewhat intuitive. But you might want to say that I want the topological boundary conditions, and I want that to be elliptic, consistent with the action, finiteness of the action, and probably that's a better way to say that, I guess. Thank you. Yes, but it's clear that at least somebody in the audience is listening very, very carefully. I'm very glad. So, okay, so this way I could, and then in fact, you can even go further because there is a moduli space of Riemann surfaces. And then you can, for example, divide the Riemann surface in 2, for example. And then see what happens. Well, of course, it's a decomposition of the Riemann surface. And of course, each Riemann surface defines integrable field theory. So morally speaking, in this situation, what you should get is that there are 2 integrable field theories and glued together. And glued together roughly means that you do the gauging. So there's the global symmetry gauging. And so we are not necessarily talking about a particular integrable field theory, but integrable field theory with parameters, first of all, but also not just a single, even a single theory with parameters, but a collection or family of integrable field theories. That's what we are discussing now. Well, let's see. Well, that depends on the, for example, if you maybe, let's see, there are 2 types I explained in this particular talk. For example, there's a Gross-Nouveau type model, and that's one thing. And then there's a principal Carter models and Wess-Mino with principal color model, non-conformal WSW, if you like. And here, in this case, it's just about one copy, but you can actually try to have multiple such defects. And you get a version of the multiple copies of WSW coupled in some way while preserving integrability. That's another prototypical example. But you can also try to do other defects. You have something called a beta gamma defect, and you get the coset signal models, and et cetera, et cetera. So you can, so we actually haven't pushed the boundaries too far, but yes, but there is some discussion of that. And maybe if there are some experts, later, Benoit Bicedo and others extended this to incorporate the so-called something called the Krimsik model. And that's a very general type of signal model where you can discuss the T-duality. And that's it. Yeah, so that's also another cluster model. So, yes. Yeah, so it's like so there is a gauge field G inverse dg, and then there you can write down cubic term of G inverse dg cubed. But that's a three-dimensional thing. But you can define it by starting with a 2 manifold and then take a bounding 3 manifold, and that's and then you can argue that the choice is independent of such a bounding 3 manifold. So that's so that's on topological. So in other words, it's a topological term which you can write down when you write down two-dimensional theory. Let's see. So that's how it works. Oh my god, time. So I see. I still have some little bit of time. So let's see what I'm going to talk about. Yeah, okay, maybe I can continue. Okay, great, thank you. So let me try to discuss next. Okay, so here I discussed two stories. Maybe I was too fast, but at least it's clear that I've discussed integrable lattice models and integrable field series. And these are described by one-dimensional defect and two-dimensional defect. But of course, it's natural to imagine that these two are related. And in fact, that's one of the most canonical questions in lattice models. If you have a lattice model that's known as U-view theory typically, and the question is that to which infrared theory it flows to. Or if you turn things around, if you start with the integrable field theory, then how you discretize it in such a way that you get integrable lattice model. And in fact, that was historically one of the motivations where Fadeev and others started looking at integrable models as far as I know. They were interested in integrable field theories, and they started discussing integrability as a way to UV regulate the quantum field series. And of course, so the relation, if you stare at this, the relation is kind of clear. You just take the lattice spacing to 0. And of course, the point is that that's usually involves the renormalization group flow, which is a very complicated procedure. But fortunately, very fortunately, in our setup, it's actually much simpler because instead of talking about the 2D theory, I have a setup where we have a 4-dimensional theory coupled with a 2-dimensional defect. And the 2-dimensional defects are extremely simple, just a free theory. So it turns out you can discretize easily. And so it's almost like you do nothing. So there is this, for example, this is the example of the chiral defect. And there's a del bar. But this is a holomorphic theory, which means that there is a derivative only along one of the directions. So you can trivially discretize in the transverse direction, or orthogonal direction. And you get the one-dimensional defect. And the same, but of course, depending on whether it's chiral or anti-chiral, you have to discretize in a different direction. In the right cone direction, and then you get the lattice. So what you get is indeed a light cone lattice of one-dimensional lattice. One-dimensional defects, one-dimensional lines in the light cone direction. And it turns out that this is precisely the picture which some people, including Fadeev, Reshetkin, Volkov, and others, were interested in, known as the light cone discretization of integrable quantum field theory. And incidentally, there is some interest in this from the viewpoint of quantum simulations, which I'm following up. But anyway, so we reproduce some of the features, but now the procedure is much more general. So for example, you can take various different defects of the different type and then try to discretize and have a more intricate structure. There are some ambiguities to how to discretize, but they all should flow to the same integrable field theory. And so on and so on. Yeah, that's what's called the topological direction, which now becomes a holomorphic, yes. Yeah, that's previously called the topological direction. Yes, but now I include a holomorphic surface defect there. So it's no longer topological, but yes, that's where the integrable lattice model lives. Yeah, so you first get a bunch of lines, and this is a one-dimensional defect. Now, there's one more statement that you get a one-dimensional defect, and you can ask, okay, so it's a specific Lagrangian, it's this, but you can ask like, can you trade it for something else? That's right, yes. Well, let's see. So yeah, here after discretization, yes. Let's see. So here it's along the W direction. So sorry, maybe I made a mistake. So yeah, so it's along the W, or maybe there's some mistake in notations. Yeah. So yeah, yeah, W is a holomorphic direction. So yes, yes, one real variable. No, sorry. Okay. But holomorphic direction becomes it really becomes a one-dimensional defect. So one-dimensional dependence, one-dimensional derivative. That's what you get there. So W becomes a one-dimensional direction. So yeah, differential along the line. Yes. So no longer holomorphic. So yeah. Yeah, that's right. So yeah, not the real part. So it's more like yeah, along the W direction, I guess. Yeah. So yeah, so I think that, so let's see. One of the directions, okay, maybe the sigma minus, in fact, what does it mean? So, but anyway, so you have the W derivative and the W bar direction, which is transverse, for example. And then W bar direction you discretize, and you only have a W. So once you discretize it, you only have W literally. One-dimensional thing, one-dimensional derivative, one-dimensional dependence, one-dimensional everything. And the W bar dependence is really discretized. Now, you get a simple defect, yes. So, and then, so what does it correspond to? It turns out that you can evoke some mathematical results. Essentially, this Borel-Biot version of the Borel-Biot theorem, which says that, in fact, you can try to have, so this is one particular chiral defect. But if you try to discretize, you get something, one-dimensional defect. But it's something where the gauge field couples to. If you like, there is some group action on that thing. And it turns out that you can trade it essentially for this Wilson line, which is the ingredient which we started this point, discuss the integrable lattice model. So in general, I have an integrable field theory, etc. But in many cases, you discretize, and what you get is the Wilson line. Or in other words, there's a label for the representation, and that's enough to recover what integrable lattice model you get. And so this, okay, so I try to finish, and then that actually raises a lot of questions. So there are different type of defects, but essentially, if you keep track of the group action, you can trade it for the Wilson line, so which is a simple object. So many different looking defects, but if you discretize, you land on the same thing. Which means that all these things, after all, should give rise to the same theory. In other words, they should give rise to the duality, or the web of dualities in integrable field series. And in fact, that's how it works. So a lot of defects, but all these defects collapse to the Wilson lines. And then you can try to realize. So you can try to, and then that means that you can convert one defect to another. So maybe let's see. For example, this is a schematic picture. So here, this is a schematic picture where you have two defects. One defect, another defect, 2D defect. And what I said that if you discretize, it just corresponds to the same object, which is the Wilson line. So you can actually replace one defect by another, defect-wise. And you get the different looking theory, etc., etc. And then once you have that set up, then you can go back to the effective two-dimensional theory by integrate out the gauge field. And it turns out that you can realize many of the non-abelian dualities, non-abelian bosonizations, etc., using this framework. So it not only clarifies the relation between lattice models and field theory, but also it explains why there are non-abelian bosonizations or other dualities among two-dimensional integrable field theories. So let's see. So I think I think I prepared way too more material, but let's see. So let's see. So maybe this is the final word. So a little bit over time, but so here I explain how the four-dimensional Chern-Simons theory explain lattice models and field theory. But you can actually even go further, 60 theory, etc., and you get the Masahito Yamazaki equation. And that gives like a different type of integrable equations, like a KDB or so. So the fascinating is that different aspects of integrability. And their integrability defined in a different sense. So a priori, there are no connections, but it turns out many of the ingredients of integral models come from the same ingredient, which in this case is 60 holomorphic Chern-Simons, or even other, like a 10-dimensional Chern-Simons, holomorphic Chern-Simons theory. And so this shows in the spirit that that we have the fusion of mathematics and physics. And I said before that integral model sits somewhere in between. But I think it's a little more than that. So integral models is actually a kind of a group. So it used to say that Freeman Dyson wrote a famous article that there was a divorce between physics and mathematics. And but you need some mediator, right? So to remedy that situation. And integral model has been one of such ingredients. So with that, it's really an honor for me to talk about such connections on this occasion, celebrating the mathematics and physics of today. Thank you.
So thank you very much for this amazing presentation. Are there any questions?
Thanks for the talk. How about the tetrahedron equation?
Sorry?
How about the tetrahedron equation?
Tetrahedron equation.
Could you use
I think that's a very interesting question. Obviously, I mean, certainly, a lot of people ask me, and I have thought about it. But I think that's an interesting question. And I mean, let's see. Well, the first thought it comes to mind is that you can literally try to replicate many of the things I said. You can just change the dimensionality and things like that. You change the branes and everything, and many of the things may work. That's the first thought. And it might be tempted to write a paper that effect, etc. But then the second is that now if you look at the actual solution to the tetrahedral equation, first of all, there are very few. First of all, well, of course, it might mean that there are new solutions which we have found. But the third, one more thing is that integrability 3D is a completely different beast. And that's because, for example, if this type of story goes, you can go to integrable field theory in 3D, for example. But at least in the usual assumptions, Coleman-Bandura theorem forbids that, actually. So there are some concept charges, and it's not internal symmetry. And then if there's a system's gapped, etc., asymmetry is trivial, for example. Well, you can debate the assumptions. So that means that, I mean, you cannot actually hope for the integrable field series in 3D in the standard sense. Of course, there are some exceptions, like 4D equal 4 is integrable, but only the primary limit. So for example, etc. So there could be a subtle sense that things are, but at least if you flow all the way to field theory side, it's very, very subtle. Of course, it's also the same case that there are amazing set of works, for example, by Kuniba and others, for example, about the quantum group and solving tetrahedral equations. And some of that has a good feature. And in fact, one of the potential ingredients is try to use the two-gauge groups and things like that, which, for example, Hank and others and Joaquin and others have been working on. So maybe it's a two-categorical type, two-group type thing might be a good solution. But of course, at least I have a mixed feeling. So some aspect, it feels that you can do purely formally. But on the other hand, as somebody who has been working in the model, I know the tetrahedral situation is very, very different. And the question is that, so if somebody writes a paper that, okay, just change the dimension of the brain, explains, it's great, but I'm a little skeptic just with that. So if you can somehow reconcile the practical solutions of the tetrahedral equation with these general explanations, and then I'll be very satisfied.
That is that your group scattering some produce this.
In fact, I mean, So in fact, let's see. For example, some version of that was done in a slightly different context. For example, you can try to go 5D Chern-Simons theory, for example. And in fact, Hao and others have written a paper about that. And then doing probably the same type of thing you know very well, like a Miura transformation. And then there you have a surface defect, for example. And you have some version of computation in a slightly different context, for example. So, it may work. It may work even for the tetrahedral equation. But I want to be cautiously optimistic on that. And,
I think we have many questions. Yes. So many questions, but we have to finish.
We might have to go to the math night, but yes.
happen if maybe I missed it? What happened if you put boundary times sigma?
Yeah. So that's also a good question. And then what you expect is that you get the boundary Yamazaki equation, so-called the reflection equation, so-called. And so there you get the boundary and you get the reflection equations. There's, in addition to R, there's something called a K, which is the reflection matrix. And then there's a boundary Yamazaki equation, which is of the form KR equals to the other order. And that you can try to derive. And in fact, there is a nice paper by David Skinner and a student who did part of that. Now, there's some aspect of story works, but other aspects seems to be a little bit more involved. For example, as far as I know, if in that story, the leading term in the R matrix is not the identity, and it's a little bit more complicated functions and things like that. So there's a little bit more subtle, and it also even representation theory wise, not everything is understood too clear cut not in a complete satisfactory way. For example, even the quantum group, there's something called the I quantum group, which is related to these reflections, which people, some mathematicians are discussing, but even for the quantum group itself, not the quantum affine, for example. So, but the short answer is that there is a paper and you can do some part of the story.
Question?
Yeah, I have many questions, but I'll
We
just
can
pick the most
yeah.
important one. Okay. Yeah, sure. Well, what's the so you take the gauge group to be a semi-simple group, right? So you get a Yangian or trigonometric and elliptic versions for semi. But what about affine Yangian?
Yeah, affine. That's also a very good question. And the short answer is that you should go to 5D Chern-Simons theory. Yes.
Oh.
So yeah, in the 5D Chern-Simons theory, what's good is that in addition to H bar, there's a non-commutative deformation you can do, and there's two parameters, and that's how we represent the affine Yang with GL1, for example. And then, well, and even people try to go to GLN, etc. But now, once we'll talk about it, there's even a further generalization of the algebra known as the Quiver Yangian, which I've been working on, and that one is not reproduced from this approach.
Right, because of course there's also another approach that can ask quantum field theory to integrability that you didn't mention, that's Bethe gauge correspondence. In which case, going to affine is like not a big deal. We just take affine quiver.
I think that's interesting, and yeah, I mean there's some connections, but the gauge gradient here, it's trying to highlight the different aspects, whether you solve that in the beta ansatz and solve it. Here it's about to identify the model itself, and then of course there is a clearly overlap, and then some situation there's a cigar, for example, if you try to realize. Yeah, that's right. So you can relate it to string dualities, and then you can make sense of that. But yes, yeah, but we can discuss some further details. Yes.
We take another two questions, and then, of course, the speaker, I'm very sure, can discuss afterwards.
Yeah, I'm happy to.
The talk is very exciting.
Yeah, my question is, there is another large class of integral models known, which has many features in common, called affine Godin models. By the affine Godin models, Fagin and Frankel have introduced, which also have a massive in which you have. So I'm wondering what's the relation to the models that you can describe. So is it so more specifically, can you get all of them using the 4D Chern-Simons, and can you get more?
Literally all of them, but more or less the answer, yeah, I'm not sure literally all of them because I don't know exactly what is known there. But there's a nice understanding that, so this is, I kind of formulated in the Lagrangian description, but you can do the Hamiltonian quantization of the theory, and then you can show that if you do the Hamiltonian quantization of the theory, it reduces to what Bisedo and others are working on his affine Godin model approach to integrable field series. And then, so you can make a connection by switching between Lagrangian formulation and the Hamiltonian formulation. And so yeah, so it's tempting, in fact, to try to make a connection to Lagrange and everything, for example. And certainly there's some discussion of the connection to ODIM, for example, and the RG flow, for example. So yeah, but the short answer is more, yeah, it should be yes. I'm not completely sure if it's literally everything, but.
You know that not every representation of Lie algebra can be lifted representation of, let's say, Yangian.
Yes.
This means that you cannot do trace Friesen-Linear representation.
Yeah, so let's see. So that's related to some of the anomalies, for example. It's related to this two-loop diagram, which is a little bit far too many slides. But yeah, so for example, if you start, for example, one favorite example I have is that if you have a 248 representation of E8, it doesn't uplift to the representation of the Yangian. You have to add what Presley and Seagal, called the pre-fundamental representation, which is 248 plus 1, 249, for example. And that sort of subtlety arises partly related with the two-loop anomaly. So you can show that using this relation that such things are necessary. In other words, it's a version of the gauge anomaly. So some of the representation of the gauge Lie algebra, which is completely fine classically, but there are some quantum anomalies, gauge anomalies, and then so by working that out, you can match with the representation theory.
So maybe like my simpler question will be, then if it won't do Chern-Simons, just some gauge theory, like some other gauge theory.
Okay.
Are there also gauge anomalies which prevent us taking Wilson linear
Well,
representation?
in general, yeah, I mean, the way that it appears here in particular, for example, in the two-loop diagram, it's a little bit peculiar. I mean, usual quantum field theory, there is a one-loop diagram, which is the so-called gauge anomaly, and it captures many of the ingredients. But somehow, in this case, it's a holomorphic theory, etc. It's peculiar, and that's how you get it at two-loop level. Actually, we proved that there's a this anomaly in two-loop, and only this anomaly in two-loop, but we didn't have a proof that that's the case in all orders in perturbation theory. So, but if you look at the Angian relation, that's not the case. But my point is that in general, it could arise at any loop order, like a 10 loop, for example, it might appear. But a priori, but in typical case, it's just one loop, and in this case, it's just two loops. And but if you exhaust more and more general theories, like this is a holomorphic theory in some direction, crazy theory, then I don't necessarily know a priori, other than doing the BRST cohomological analysis, to show that whether there is a anomaly or not.
So I see that there's still more questions, but I'm very sure that he can discuss with you personally afterwards. And I would like to close this afternoon session and tell you that tonight,
Thank you.
we thank the speaker again.